Okay, Physics 30s, this is going to be a quick video about cathode ray tubes and how to solve for various parts of a cathode ray tube and a magnetic field. So this is actually specifically in your workbooks as promised. This is question 7. So question 7 on page 288. Okay, so scenario is, as we've been through this many times already, that there's some kind of accelerator. Actually, we'll put the gap on this side. Some kind of accelerator, and there's some electrons over here, and they are going to be accelerated through a gap. So this would be a positive plate, and that would be the negative plate. And these electrons are going to fly through the gap, and they're going to continue on in this direction. And the assumption here is that they're going to have a uniform velocity. So the velocity is going to be the same all the way through this scenario. And that's crucial. That's a really important piece of understanding, because as it comes out of this side of the plate, there's going to be some kind of magnetic field. So we can imagine that there's a magnetic field like this, which would imply that it's going into the page, and this would create a force on the electron. We can in fact do our quick hand rules, and so my thumb is going to represent the movement of the electron, my fingers are going to go into the page, which means my hand is pointing down, so the force magnetic here is going to make this electron curve continually, and it's going to start off curving downwards, but it's going to make it do this. Okay? And that's really important, because that means that at this point the force magnetic is going to be the same as my force centripetal at this stage. Okay, now the question, as we read it through, it gives us some information. It tells us that we know the potential difference. So we know the PD across the gap here, we know that to be 1200 volts. Okay, so there's 1200 volts across the gap. And we are also told that the magnetic field, so B, is 0.045 Teslas. 0.045 Teslas. In fact, I don't think you can see that there, so let me write that in a different place. Let me do that over here. B, 0.045 Teslas. Okay. The question is, what is the radius? So what is this curvature of the electron? So what is R? Okay, so there's a series of conditions here that we really need to be getting good at by now. We've seen this already with mass spectrometry. It's the same in this section. The conditions are as follows. Here's your potential difference. Okay, this is an electrical potential difference across the gap, and this is going to tell us that we can figure out the electric energy, the energy that we have in the electrical system here. So I'm going to say that the electrical energy is going to be equal to the energy given to the electrons, and the energy given to the electrons is going to move them. It's going to give them some motion. They're going to go from 0 velocity to some other velocity over here. So it's kinetic energy. Okay, and this should be looking very familiar. Electrical energy, as we should know already, this should be a given, is VQ, voltage times the fundamental electric charge, and that's going to be equal to the kinetic energy of the electron. Very important. Remember, the key here is this velocity. This velocity doesn't change. So what we're going to want to do here is rearrange this to solve for the velocity. So you can do this step by step if you want to, but I'm just going to write it down. I get this to be the square root of 2 VQ over m. Okay, so that's my velocity condition for this first piece. Now if I follow this on, I'm going to use red here for this next scenario. If I follow this on, I have a condition that I've already stated, which is Fm is equal to Fc, so force magnetic is equal to force centripetal, and that's going to give me my condition here for the circular piece. So in other words, my force centripetal is going to be mass times velocity squared over r. This is a force centripetal formula that we've seen in physics 20. And my force magnetic is, well, again, we've seen this in unit B, but there it is, QVB. Okay, what am I trying to find out? Well, I'm trying to find out the radius. So there it is, there's my radius. Q is a given, B is given in the question, mass is a given, it's the mass of the electron, and the voltage is the one thing that the velocity is the one thing that I do not know here. But over here I said that since the velocity is constant, this must be the original condition, so whenever I see velocity I can just replace it with this formula here. So that's essentially what I'm going to do. I'm going to basically merge these two together. Okay, so and solve for r. What does that look like? Well, you can do this yourself, but basically I'm taking this and I'm putting it in for velocity. Now, I've got two velocities here, so could be slightly confusing, but I'll save you all the steps and just give you the end formula for r, and then hopefully you can go back. If it's not clear, you can do it yourself and figure out the steps. But the formula here for r, given our two conditions, is going to be the root of 2v, so 2 times the voltage times the mass, over the fundamental charge times the magnetic field squared. Okay, and you can do the math yourself, but if you plug it away, putting in this for B, this for voltage, mass is the mass of the electron, which is given on your data sheet, and Q is the charge of the electron, which is also given on your data sheet. That's going to give you 0.0025977 meters. Okay, which seems to make sense because the keyed answer is 2.60 millimeters. Okay, so that's to 3 significant digits, and I think that makes sense because although this is 12, actually this is given to be 0.0450. So there's 1, 2, 3 significant digits there. So my answer is also in 3 sig digs. Okay, that should be something that's becoming very familiar to you by now. If it's not, go through it again, make sure you can do it. There's a couple of follow-up questions on that as well, or you could of course go back to the previous stuff we did on mass spectrometry, and you can do this stuff again. But this should be by now very, very clear. It shouldn't take us very long. It should just be bish, bash, bosh, and away you go. Okay, thanks for watching.